Good morning, dear students. Welcome to another session of micro and antennas. So, in previous session, we completed a discussion pertaining to antenna aspects, in which we discussed different parameters such as, say, what is meant by radiation pattern, radiation intensity, power theorem in terms of power density, and power theorem in terms of radiation intensity. So, these were a few things what we discussed: directivity, gain, then what is meant by, say, radiation resistance. Then we saw what is effective aperture, what is the maximum effective aperture of two of the antennas. Then we discussed regarding Frisch transmission equation. So these were few things what we discussed. So that was pertaining to the antenna basics. So now in this session, right, in probably in another 2-3 sessions, I'll be trying to discuss concepts pertaining to the strip lines. So in So in this strip line, we had seen that previously we discussed derivation pertaining to the transmission lines. So in which we had obtained Z naught, gamma, alpha, beta. So these all parameters in terms of RL, GC parameters. So that is your conventional transmission line, which is used for say transmission of the microwave power. Now, when we come across the other aspect, right, we have something termed as strip lines or microstrip lines, which help us to again transmit say, the microwave power from one point to the other point. But this is done with the help of some semiconductor profiles, or what we call as solid state devices. With the help of solid state analysis, we try to achieve this. Now, what is actually a solid state device? So if you refer to ICs, right? If you're referring to IC, that is integrated circuit. So in integrated circuit, you observe that you have the semiconductor material on which you put forth the different say semiconductor devices. Like you try to implement the transistors onto the integrated circuit. So that is nothing but the microstrip elements. But in this case, what happens is, since you're dealing at high frequency, because of which it turns out to be a high power parameter also. So when we are dealing with high frequency, I cannot utilize the same material which is being utilized for developing, say, the transistors, and that is a, say, BJT transistors which you use in your lab, which previously in communication labs and all you are using, right? So those we cannot utilize. So we should modify those things. Say you modify the material what is being used. So based on that, we build the strip lines. So in this case, what is actually a strip line? This is also built using the integrated circuit concepts. Now here we can observe in this case, so we call it as monolithic microwave integrated circuit, MMICs. So integrated circuits refers to your the other integrated circuits in general, what we term, say, or if you're using in logic design lab, right? That is digital electronics. So in that you're using ICs, you're operating at very low frequencies and very low power. So those cannot be used at high frequencies. So I have to do some changes. So what has to be done based on that, we have to look forward. And the name tells that it is strip lines. So this is the lines which are developed using the substrate or the material for that specific purpose. So this strip line basically helps us to connect the devices, integrated devices. Say I want to make a connection with the diode. So how I can do it? I can do it with the help of a strip line. I can do it with the help of the strip line. So that is so these strip lines which we are talking of, we classify it under the monolithic microwave integrated circuits. So again we can have multiple classifications in this. What are the other classifications in this one? We have the micro strip lines, we have the parallel strip lines, we have the coplanar strip lines, we have the shielded strip lines. So these are the four parameters what we'll be discussing in this case. So it is basically what happens is when you consider say wired kind of structure, that is a transmission line, it will consume a lot of space. But when we go for the micro strip or strip lines, right, it reduces the consumption of the area what we look forward. So it is a miniature version of those transmission lines what we had discussed in the previous sessions. So strip lines are the miniature versions of the microwave circuits what we are talking of. And when we are building these, right, we make use of the thin films or the photolithographic techniques in order to develop these microwave strip lines. That is IC is what we are talking of. So these monolithic microwave integrated circuits, again, they're classified into these four aspects. That is micro strip lines, parallel strip lines, coplanar, and shielded strip lines. So these are a few of the things to name around. So this is how a strip line will look like. So it will look like, say, something like a integrated circuit in which this acts as a transmission line for me. So therefore, we specify it as a strip line. So using the strip line, right, I can transmit the microwave power from one point to the other point. So this will be acting for that purpose. Now, when we are talking of this, you can observe that this microstrip which is present, it is having a thickness of T. It is having a thickness of T, and there is a dielectric substrate which is present at a height of H. So the height of this dielectric material or dielectric substrate is H, and this H is actually measured from the ground plane. So it is like the reference point. It is like the reference point. And the width of the strip line is given as W. The width of the strip line is given as W. So in this is the schematic representation of the strip lines. Now what happens is when you pass current through this, and the current is passing through this, or when you have a magnetic field associated with this, what happens is it gives rise to the current, so which in turn gives rise to the electric field. So when we consider this, right, this is how the field lines will be appearing. Now, what happens is because of the current flowing through this, there will be a magnetic field, there will be an electric field associated with this strip line. So, when we observe those aspects, right, what happens is the field lines will be passing through the substrate to the ground. It will be, say, from the plus to the minus. That is what we had seen. So, it will be moving from the substrate to the ground plane. Now, what happens is, if you just observe, these field lines are not confined only to this substrate. That is, only they are not confined only within this substrate. They are actually present even outside. They are present even outside. So, if they are confined within, right, we term that as transverse electromagnetic waves. We term that as TEM waves. But what happens is, it is not entirely confined within. It is confined even at this point and even at this point, because of which we term the field as quasi TEM waves, quasi TEM. So that is, in that mode it will be operating. And when we consider the field lines, the field H field is at 90 degrees with respect to the E field. So based on that, these field lines will be represented. So this is what a strip line will look like. It will have a dielectric substrate, and the substrate relative permittivity is given by epsilon r, and this substrate's height with respect to the ground is h, and this h is nothing but where the height at which the microstrip is present. Sorry, the strip line is present. The strip line width is considered to be w, and this is the thickness of the strip line what we are talking of. So with respect to this, right, this is acting as the transmission line for me in your microwave devices. So that is in your integrated circuit. So with respect to this, what happens is, on this I can mount the different devices and make the interconnections and try to operate the entire microwave system. So this is how it goes around. And what happens because of this is, because of this, the structure of the device gets reduced. So that is what we can observe. So in this part itself, I discussed regarding the microstrip lines. So that is this explanation pertaining to the microstrip lines. So sometimes microstrip lines are also called as open strip line. So they are also termed as open strip line. Now, in this case, your conventional transmission lines can be your coaxial lines or the waveguides. What we had spoken in the previous sessions. So, in that, we could see that power transmission happens with the help of these coaxial lines or waveguides, which are your conventional transmission lines. But when we consider microwave devices built on solid state analysis, so that is your solid state device. So when I consider this, what happens is these transmission lines, I can convert it into these forms. I can look forward for implementation of the same concepts using these solid state devices. Solid state devices are nothing but the integrated circuits what we are speaking. So how the integrated circuits are built, they are built based on that solid state analysis. So if you want to have a diode, right, you have to take a substrate. Say you have to take a substrate, p substrate. If you want to build a transistor, you take a p substrate, you each the region, and then you put the n material and the n material at the other end, then you build the transistor. So in the similar way, we can have the building of this strip lines, so which we term as the microstrip lines. So these are the microwave strip lines what we refer to. Then the quasi TEM what I spoke over here, we can just observe over here the modes in which this microstrip lines operate. We term it as the quasi transverse electromagnetic waves. Why it is termed as quasi? Because you can see that the field lines are not only confined within this region, they are even present outside the substrate, because the field lines have to emerge from one point and then end at the other, say emerge from positive and end at the negative. So that is how your field line appears. So this is because of that it is termed as quasi TEM mode. So then apart from this, what happens is, since we have structure which is given in this kind, we can have different microwave integrated devices which we can connect to this that is using this strip line or microwave lines, microstrip lines. We can connect different microwave devices to these. So these are basically acting as what? They are acting as the transmission lines. So next, what are the characteristics pertaining to the characteristic impedance pertaining to the microstrip line? So when we consider the microwave strip lines, right, which is in this form, what happens is it can be represented in this form. So in this, again, you can see that this is the ground plane. From this, at a height of h, I have the microstrip which is present, which is of the width w, and thickness of the strip is t. The substrate material which is present in within this region is having a permittivity, that is relative permittivity of epsilon r. Now, if I have to represent, generally what is done is such kind of microstrip lines are represented in the wire over ground representation. So this is like you have a wire which is at a height of h from the ground, and the say relative permittivity of the material which is present between the wire and the ground is epsilon r, and d is the diameter which is pertaining to this conductor. So what is done is this is actually a rectangular waveguide kind of structure. So when you're analyzing, what they do is they convert this representation into a wire like structure, and then the analysis is carried out. So this is a wire over ground line. So this is similar to whatever you are looking forward over here. So this is used to say connect the devices. This is also used to connect the devices, but the representation is in this form. So when we consider this concept, what is so basically what we are doing is we are trying to obtain z naught of this one from indirect method. That is, we try to obtain z naught of this, and then we apply that the concept to the microstrip line. So this is actually called as the indirect method of obtaining, that is the comparative or the indirect method. So these if I want to know what is z naught, right, you have to refer to the transmission lines and waveguides aspect, and from there you will get to know how this equation comes into existence. So based on that, we uh, we obtain the characteristic impedance of this microstripline, what we are discussing, as z naught is equal to 60 divided by square root of epsilon r into natural log of 4h by d. And when we are considering this equation, right, we have to see that h is much greater than the diameter. That is, this height is much greater. That is, this height what we are considering over here is much greater than this diameter of the wire what we are looking forward. And this height in this case, it is measured from the axis to the ground point, from the axis of this conductor to the ground point. So this is what z naught implies. So in this, what are the parameters? Epsilon r, which is the dielectric constant in the ambient medium. Then we have the h, which is the height from the center of the wire to the ground plane, and d is the diameter of the wire. So this equation is obtained based on this. So this is the comparative or the indirect method from which we obtain the z naught. Now here what we do is we make some changes in epsilon r. So if you observe over here, what happens is what is the effective substrate which comes into existence? That is what we have to look out for. So based on that, we have to make some changes over here, and based on that, the changes happen over here, and we see what is the z naught for the microstripline based on the comparative method. So here, what is the effective dielectric constant? So in order to, if you just observe what we have is, we have effective dielectric constant, which is given as 0.475 times epsilon r plus 0.67. So this is the equation which is obtained from the empirical equations. From the empirical equation, we obtain this as the effective dielectric constant. So now what we do is this equation. So here we can observe that Z naught for the wire over the ground is given as 60 divided by square root of epsilon r ln 4h by d. Now here, what changes we have to look out for is we have to make a substitution for epsilon r and the diameter in terms of these parameters. So h is the parameter which is present. Epsilon r, I have to check out and replace it with appropriate value. Then apart from that, this d parameter is for the circular wire. I have to try to get a replacement in terms of t and w. So this is what we have to look out for. So this is the Z naught value, that is intrinsic impedance for the wire over the ground transmission line. So when we consider the comparative method, the effective dielectric constant for the waveguide is given by epsilon Re, which is 0.475 times epsilon R plus 0.67. So this is one substitution. Then apart from that, I have to make the substitution of D. So for rectangular waveguide, we have the thickness and the width of the strip line, which is given over there. So in order to replace that, we can utilize the diameter of the wire, which is given by d is equal to 0.67 times w into zero point 0.8 plus t by w. So this is the diameter related in terms of thickness and the width of the strip line. So what we do is we substitute these two equations, epsilon re and the d equation, in the z naught equation what we had observed here, that is in this equation. And when we substitute and simplify it, right, when we substitute and simplify, we end up having this parameter, that is, you can observe here. So z naught, in this we have replaced epsilon re with the equation what we had seen over there, that is 0.475 epsilon r plus 0.67, and we had replaced d value with its relevant equation. And when we simplify this entire parameter, we end up with Z naught, that is characteristic impedance for the microstripline. We obtain it for the microwave stripline, microstripline. So that is Z naught is given as 87 divided by square root of epsilon r plus 1.41 natural log of 5.98 h divided by zero point 0.8 w plus t. And this is valid when h is much lesser than zero point 0.8 times w. So based on these aspects, we have this representation. So here we can see that we have this condition. So substitute d value and try to obtain the equation in terms of h and w condition. So based on that, this is the equation what you will be obtaining for characteristic impedance equation of the microstrip line. Okay. Now, what if the width is much greater than the height? That is, in this case, we observed that. So if we consider, what if the width is much greater than the height? So if that is the case, then Z naught is given by this equation in which we have Z naught is equal to h by w into square root of mu by epsilon. But what is mu by epsilon? Mu by epsilon is again relevant to the intrinsic impedance. Now, since if we consider a non-vacuum, then in that case, mu will be replaced with mu naught into relative permeability, and epsilon will be replaced with epsilon into epsilon r. And as we know, square root of mu naught divided by epsilon naught is nothing but the intrinsic impedance of free space, so which is 377 ohm, or it is 120 pi ohm. So when we make these substitutions, right, what we have is Z naught is given in terms of 377 divided by square root of epsilon r into h by w. That is when we simplify this overall term. And if we consider that relative permeability is 1. So if we consider these parameters, this is the Z naught what we obtain. So this is when W, that is the width, is much greater than the height parameter, which is referred in the microstrip line. So this is what we have for characteristic impedance. Then apart from that, with respect to velocity of the wave which is propagating in this dielectric material, so if I happen to observe this, we make use of the equation C by square root of effective dielectric constant. And when we substitute this parameter, the C value, we obtain that it is 3 into 10 raised to 8 divided by square root of effective dielectric constant. So this is what we'll be getting for the wave velocity which is propagating in the microstrip line. So these are the equations which are pertaining to the microwave strip lines.